Vikas, is there any problem?
The Indian Association of Structural Engineers, also by a group of senior professional structural engineers from all over the country. IST is registered under the Societies Registration Act 21 of 1860. IST is a national apex body of structural engineers in India with a mission to promote structural engineering profession and cater to the professional needs of the structural fraternity. In the short span of 2 decades, association has attained an eminent position in the professional field. Its membership is valued very highly in the profession. Since inception, IST has been led by eminent structural engineers like late Sri Mahendra Raj, late Sri Kumar Ghosh, Sri Subhash Chand Mehrotra, Professor Mahesh Tandon, Alok Bhaumik, Sri Manoj Mittal and Professor R. Pradeep Kumar. As its president, IST is a permanent member of Engineering Council of India and interacts with the government on professional and policy matters related to civil and structural engineers. To expand its reach, IST has collaboration with various international professional like-minded associations and institutions. IST's primary objective is supporting and protecting the profession of structural engineering by upholding professional standards and acting as a mouthpiece for structural engineers in India. IST endeavor to ensure that its members develop the necessary skill in structural engineering and work to the highest standards by maintaining a commitment to professional ethics and standards. IST is actively engaged in organizing several continuing professional development (CPD) courses for structural engineers to help them update their knowledge and advance their career paths. It also conducts refresher courses for young and practicing engineers and student-oriented programs. Seminars, workshops, conferences, technical lectures and discussions related to the latest technological advancements and case studies are also organized regularly for members to enable them to continuously update their knowledge and skill set by interacting with the best minds from the industry. IST's activities are widely appreciated and known for quality technical contents. IST is also actively engaged in publishing its quarterly journal Structural Engineering Digest (SED), code commentaries, professional guidelines, and a monthly newsletter. IST's publications are becoming popular with time. IST has representation in various technical committees of BIS and IRC as well. Its members are actively contributing to National Code of Formulations. In the year 2020, IST started National Awards competition to stimulate interest in the structural engineering field and to promote innovative thinking and creativity. The awards are presented to the winners in recognition of their outstanding contribution to structural engineering in the categories which include Outstanding Structure, Outstanding Structural Engineer, Outstanding Woman Structural Engineer, Promising Young Structural Engineer, and Best Master's Thesis in Structural Engineering. IST is currently operating from 4 regional centers, namely Eastern, Western, Northern, and Southern, having its headquarters in Delhi to inculcate the professional culture and provide handholding to the budding engineers. IST has its student chapters in several leading engineering institutions as well. Membership of IST is open to all civil and structural engineers engaged in structural engineering profession. Members are elected based on their qualifications and experience in different grades as per eligibility requirements prescribed in the bylaws. Each application is carefully scrutinized before electing the members. More information about IST is available on its website www.istruct.co.in.
Okay. Because I think there is something popping up in the screen. I think that you have to stop. Okay. Okay. Hello, everybody. Good morning. Good morning to Dr. Natasha and others from the other parts of the world. Good afternoon and good evening to one and all. Uh, I welcome you all to this webinar, which is on a very important topic, that is the role of structural engineers in the climate crisis. Very thankful to Dr. Natasha Watson from Bureau Appalled, who has kindly agreed to share her thoughts and wisdom on this topic. My name is Alok Bhaumik. Many of you would know me. I am the past president of Indian Association of Structural Engineers and currently chairman of the Publication Committee and the Professional Issues Committee. I think you all will agree that this is the topic that we have chosen for the day is extremely relevant for the structural engineers who are involved in planning or design or construction. As we all know, we are in a climate crisis. Let's have no doubt about it, because the way things are going, we can expect unprecedented rise in temperature or fall in agricultural productivity. We have seen, unprecedented flooding in low-lying areas. We have seen, different incremental distribution of rainfall, which could mean a long period of drought in some other places. All these we have been witnessing over last few years, decades, and all of these will impose a lot of burden on us, both, from economic point of view, social or environmental point of view. And the sad thing is that, there is nothing we can do individually about it. That individual efforts alone will not change the situation at all, because we are living in a interconnected world. The situation will only change if there is a global response, a collective response to tackle the climate change. And that is, of course, happening in some kind of a global format. We all know that in the United Nations, IPCC, and this COP nowadays, every year we see it in our newspapers and we hear about it. We are told by scientists, a huge number of scientists, to limit the average rise in temperature to about 1.5 degree. This is something that is produced in the IPCC, and we know that to get there, we need to do something very rapidly. We need to do something which is unprecedented, and we have to change our lifestyle altogether. Only then we would be able to achieve this almost impossible target, as we can see now. But we can collectively prevent this planetary crash. We have the technologies to avoid the worst climate crisis, provided we act now. And this Intergovernmental Panel on Climate Change has charted a clear path as to how do we proceed to restrict to a temperature of 1.52 degrees. But to implement this charter, we need leadership, we need cooperation, and particularly structural engineers like us, we need to do a lot which we have not been doing. With this backdrop, let me introduce the speaker of the day today, Dr. Natasha Watson, who is a senior structural engineer from Bureau Appalled, embodied carbon lead for UK structures. She graduated from the University of Bath in 2010 and completed her engineering doctorate in low impact building materials in 2016, and has become one of the experts leading the development of knowledge on the embodied impacts of construction materials within the construction industry. She is the UK embodied carbon lead for structures. She has taken the responsibility to develop and deliver Bureau Appalled's advisory and consultancy services in the area of embodied carbon. This also includes upskilling her colleagues in their understanding of embodied carbon, primarily in its measurement and its reduction. In addition to the technical aspects of tackling the climate emergency, she is also actively involved in the wider issues around equity and unconscious bias in the built environment, as well as intersectional environmentalism. So she's, as you can see, she's very impactful in creating change in the built environment, though through designing more sustainable buildings, raising awareness, or advocating for a swifter improvement through policy change. Uh, Before I hand over this floor to Dr. Watson, let me just also talk a little bit about Bureau Apport, because many of the participants may not be knowing about this organization. Bureau Apport is a consultancy of engineers, designers, and advisors operating worldwide in almost all areas of engineering for the built environment. It is a business with more than 2,500 employees spread over 40 different locations across the globe. They have an office in India as well. To address the climate crisis, Bureau Apport has a net zero route map, which is very interesting. Yesterday, I was going through their website to get to know a little bit about what they do. And this roadmap is split into three areas of advisory, design, operation. And Dr. Natasha Watson is an active member of all these three areas. It can be seen that though she is pretty young, but if you go by her years of experience, she is young, but her deep knowledge, her accomplishment in such a short career span puts her in a very high pedestal. I call her a climate warrior. You know, so without any further ado, I would now like to hand over the floor to Dr. Natasha Watson for making her presentation. Over to you, ma'am.
Thank you very much. I'd just like to say thank you for your wonderful introduction to myself. It's a real pleasure to be here. It's a pleasure to speak to all of you. The fact that you're interested in this topic speaks volumes. So I really hope that your time is well spent here and that I can help set the context of our role within tackling the climate crisis. Again, sort of elevate the idea that, yes, we are all individuals, but if we collectively work together, we can have a really large impact. And also, yeah, just hopefully start you on your journey of becoming climate warriors yourself as well. So thank you very much for having me. I will share my screen and put my presentation on present mode. If you could let me know if that's working.
Yeah, it is working. Perfect.
Thank you very much. Right. So hello, everyone. Yes, I'll be talking about the climate emergency, but I have actually titled this more along the lines of embodied carbon. I will explain exactly how I got to that kind of change of title as I proceed through my presentation. The contents, I'll be giving sort of context to the climate emergency and then focusing on what embodied carbon is, where it is in our buildings, what we need to know if we think about measuring it. But then after that particular sort of technical and theoretical discussion around that, I'll be giving pragmatic and practical advice on how we can actually reduce it as well, following the four tenets of build nothing, build less, build clever, and build efficiently. I'll also be talking about impacts wider than embodied carbon as well. And then hopefully ending on a summary that you'll be able to take to work with you on Monday, so you can really start to put these steps into practice. So you've already heard a little bit about me, so I won't dwell too much on this. But yes, my engineering doctorate, my thesis was on developing material selection strategies to improve the embodied impacts of buildings. So I've been talking about this topic since 2016, and it's been amazing to see the uptake of it. I think around about 2019, it really sort of captured the imagination of definitely our UK colleagues, and is starting to be sort of accepted and accelerate globally as well. Just to kind of give you a bit of my sort of MO for my work is I focus on action and ensuring that we don't lose sight of ensuring an equitable and just transition to a low carbon future. A little bit about Bureau Happold as well. We've got offices everywhere, and yeah, we have a presence in India as well. We've been in India for around about a decade, or over a decade now. And we cover lots of different specialisms as well. I'm very happy for these slides to be shared after the presentation. So if any of you are scribbling notes furiously, just like to say that I will be sharing these slides as well. So it will be great if you could sit back, relax, and listen to the discussion and give questions at the end as well. Finally, about Bureau Happold, Mr. Alok was sharing that he'd been reading about what our commitments are. And in our latest global sustainability report, we've launched our net zero route map. And that sort of covers the fact that by 2030, our goal is to design all new build projects to be net zero carbon in operation, but also by 2030, our goal is to reduce the embodied carbon intensity of all new buildings, major retrofits, and our infrastructure projects by 50% from a 2020 baseline as well. So, context. Climate change will continue to disrupt our way of life. As you are all very aware, when COVID-19 hit, it really impacted and changed all of our ways of thinking, living, working, etc. Within the UK, we're currently suffering a cost of living crisis where groceries have increased in price like an amazing amount by sort of standards of general sort of inflation. And so there's also been sort of elements of recession as well, which also really drastically impact the way we work. And to top it all off, we are seeing the impacts of climate change today within the UK as well. We've had really unusual weather, and it's only going to get worse. So it is going to continue to disrupt our way of life. The climate emergency is in the minds of everyone. A lot of my slides will be quite sort of UK context, but I do believe that the ones that I have chosen can be translated to a more global stage as well. Within public and politics in Europe as well as in the UK, 93% of Europeans believe climate change is a serious problem. And it's around about a 2 out of 3 people within England believe we're not doing enough to tackle climate change. The UK actually has climate change refugees. So by 2050, the people who live in Fairburn in Wales will actually be underwater because they're so close to sea level. And with the planned sea level rises, the whole of that village will be underwater. So it is really affecting us in ways that I don't think that we had actually predicted. And at our last general election in the UK as well, we actually had our first ever climate debate. Granted, this was in 2018, so we should be having another climate debate in our general election that we have this year. But it really sort of speaks to the fact that it's in the minds of the public and our politicians as well. It's also in the mind of banks and financial institutions. So the United Nations Environment Programme Finance Initiative set up the Net Zero Banking Alliance back in 2020, 2021. And these figures are from around about February this year, but 143 banks had signed up to the Net Zero Banking Alliance from over 44 countries, and it represents around about 41% of global banking assets and $74 trillion of total assets. In a nutshell, the Net Zero Banking Alliance commits these banks to divesting from high carbon industries such as fossil fuels, but also high carbon industries such as steel production and concrete production as well. So you're starting to see these financial mechanisms changing how different materials are funded on a global scale. We're also starting to see changes within clients because obviously if banks and financial institutions are divesting from high carbon materials and high carbon activities, that impacts the financing of the clients that we work for as structural engineers. There's things such as funding concerns, but then also things such as public image concerns as well. There have been quite a few high profile cases within the UK where certain buildings have been pipped for deconstruction or demolition, and there's been a huge public outcry because of the carbon implications of it. And it's this kind of public perception as well that clients are really tapping into and are really thinking twice about the kinds of buildings that they put together. There are also certain targets that clients can sign up to. So there's the race to zero commitments, which are again a net zero carbon commitment. There's science-based targets, which is again a net zero carbon commitment. And then there's also the United Nations race to zero commitments as well. And then, you know, with public, banks, and clients thinking about the climate emergency, it's no surprise that us as practitioners are thinking about the climate emergency as well. Again, quite a few sort of UK focused practitioner groups here, but I'm sure that you have your own equivalents in India as well. Practitioner groups such as LETI, so the London Energy Transformation Initiative, were some of the first people who came together to really try and tackle operational carbon within buildings off their own back. There were a group of predominantly mechanical engineers who were really upset about how carbon emissions within buildings wasn't being regulated and wasn't you know, on the minds of people. So they formed together as a group to tackle this. The A exclamation mark stands for ACAN, so the Architecture Climate Network, and they are also really driving policy within the UK to really sort of bring the climate emergency into regulations so that people who are dragging their feet have to think about the climate emergency in their work. We also have something called the UK Net Zero Carbon Building Standard, which is due for release this year. I've been a part of it, but it's been an amazing effort by over 300 built environment professionals to pull together this this standard so that, you know, there's a standard set of rules for us to follow when looking at embodied carbon and also operational carbon within our buildings. There's a fledgling database within the UK as well for embodied carbon assessments for buildings. It's still very much a work in progress, but it's really encouraging to see that that's there. We also have the Construction Declares a Climate and Biodiversity Emergency. I'm currently the chair of that. So that's a consortium of structural engineers, civil engineers, mechanical engineers, interior designers, landscape architects, etc., who want to encourage and support their colleagues within their disciplines with discipline-specific ways of tackling the climate emergency. And then also, finally, we have a proposed document Z, or Part Z of the building regulations, which is a very simple, I think 3 or 4 page addition to our building regulations within the UK. So the legal requirements that we have when we're doing buildings, where we would have to legally calculate the embodied carbon of our buildings. That's been debated, I think, twice within our government. And so, yes, the progress is obviously not quick enough, but it is quicker than maybe the cynic in me had thought. So as you could probably have told from that previous slide, a lot of it is about net zero carbon. Now, net zero carbon has a definition, um, and that is to keep global warming to no more than 1.5 degrees C, as called for within the Paris Agreement, which was the agreement of countries all around the world that we need to reduce our carbon emissions. The emissions that we actually produce need to be reduced by 45% compared to 1990 levels by 2030, and to reach net zero by 2050. So that means that we have a ceiling for maximum emissions for 1.5 degrees. So we need to reduce the amount of carbon we're emitting in the first place. And then any remaining emissions are to be offset either through carbon emissions removal, which is things like planting trees, or avoidance, which is a bit more of a difficult one to sort of sum up in one sentence, but it essentially means limiting the release of carbon emissions into the atmosphere from carbon sinks that are already in place. For example, the conversion of grassland into croplands, but also capturing flue gases as well. So it's net zero because the amount of carbon that you offset has to be equal or greater to the amount of carbon that you're emitting. However, with offsetting, it's a bit of a grey area, I would say. There's a lot of discussion around how offsetting is a bit of a dark art, a bit of a murky area. And some people have called it the new colonialism, where lands that have been stewarded by indigenous populations have been claimed as offsetting when that land was already existing. And also, deep dives from journalists into these offsetting strategies have come up with some horrible findings, unfortunately, and large flaws. Also, this was from earlier this year, the world's first year-long breach of the key 1.5 degree warning limit was reported. And so, is trying to keep our emissions to 1.5 degrees enough? Should we have stricter standards? So that's a definition about net zero carbon. And it's about carbon emissions. So carbon emissions within buildings typically fall into two main camps. So you've got your total whole life carbon emissions, which is the sum of operational carbon, which is something I mentioned previously. Operational carbon are the emissions from the operation of a building. So things such as your heating, your power, your air conditioning, those kinds of things. And embodied carbon, which are the emissions from making, maintenance, and disposal of building materials. It's the carbon emissions that go into making a thing that goes into a building. So operational embodied carbon aren't equal. With more efficient building systems and also a steady decarbonisation of an energy grid, embodied carbon is already a much bigger percentage of a building's whole life carbon than before, and this is only going to increase. So that's hopefully a good introduction into why I'll be talking predominantly about embodied carbon today. Oh yes, and then also the time value of carbon as well. Carbon emissions reductions today should be prioritized over potential embodied carbon reductions tomorrow in a majority of cases. This is because we have that limit and our carbon emissions are cumulative. So if you can reduce carbon emissions today, and maybe that increases the chances of emitting carbon in 20 years, reduce it today, because that potential of emitting carbon in 20 years will have slightly better systems, will have more renewable energy, and also that assumption that you might need to emit carbon in 20 years' time might be a bit flawed, might change. So really try and prioritize reducing embodied carbon today. And then finally, to put it into context, there's a few kind of discussion words down there, but essentially, an average. This is maybe average in the UK. 6,000 meter squared office building is around about 5,700 tons of carbon dioxide, which is the equivalent of flying from New Delhi to London and back every day for over 6 years and 6 months. So your impact as structural engineers is so much greater than your impact as a citizen. And I think that when I realized this, the amount of gravitas that I brought around this topic to my profession was quite palpable, and it really motivated me to take this very seriously. And also, us as structural engineers, we need to take this responsibility seriously globally as well. Right. So a bit more of a deep dive into what exactly is embodied carbon. It refers to the greenhouse gases emitted during the manufacture, transportation, construction, maintenance, and disposal of materials used to construct a building. And despite referring to carbon dioxide, CO2, carbon dioxide is not the only gas that contributes to global warming. As you can see on the right-hand side, I've got a table of some of the many different greenhouse gases that are present within the atmosphere and present within our buildings as well. So things such as nitrogen trifluoride, which is second from the bottom there, that's present in LCD screens. And also sulfur hexafluoride is used in electrical switchgear. And those kinds of molecules, like one molecule of nitrogen trifluoride is over 17,000 times as bad as one molecule of carbon dioxide. And then with sulfur hexafluoride, like one molecule of that is over 22,000 times as bad as one molecule of carbon dioxide. So there are all these different sort of greenhouse gases that we need to be aware of, as well as carbon dioxide itself. The reason that we do refer to carbon dioxide or embodied carbon is because carbon dioxide is used as the base unit for the relative global warming potential of each of these different greenhouse gases. So if carbon dioxide is 1, nitrogen trifluoride is 17,200, etc. And that's why when you see embodied carbon units, you should see an E afterwards as well, because it's considered the carbon equivalent. Embodied carbon can come from several different sources. So it can come from chemical processes. So the actual act of breaking down limestone into cement produces CO2 as a gas as part of that chemical reaction. It can come from transporting different sort of raw materials between, for example, a quarry to a refinery to etc. And the amount of carbon emissions associated with those transportation modes is taken in to the embodied carbon. And then also embodied carbon can come from the energy and heat required for processing and manufacturing building elements. For example, smelting steel, casting precast concrete, kiln drying timber, firing bricks, but also with increasing sort of electrical and computational systems within our buildings, the production of all of that sort of electrical equipment as well. So where exactly is the embodied carbon in a building? So obviously it will really depend on the kind of building that you're looking at. But what LETI, so the London Energy Transformation Initiative, found from a sort of a typical office style building is that structural engineers are responsible for approximately 60% of a building's embodied carbon. We have an impact on our upper floor areas with our flooring systems. We have impacts on foundations. impacts on obviously the structural frame and also piling as well. And that's not to say that we don't have an impact on things such as internal wall layouts, the envelope, and potentially even external works as well. So moving on to measuring embodied carbon. So I've given you the unit. I've given you the fact that we're responsible for around about 60%, give or take. But actually, how do we measure it? I'm now going to go through a Eurocode that gives specific sort of naming conventions for all the different stages of the life cycle of a building component. And it is these kinds of naming conventions that are really common within England, the UK, and Europe. And we're seeing it being adopted within the US as well. And I believe that there are moves for this particular Eurocode to become more of an ISO standard as well. So it has a more global reach. The reason being is that within Central Europe, they really sort of spent time and dedication to really trying to standardize the calculation of embodied carbon. And I think that the amount of trial and error, the amount of iterations that they've undertaken has meant that it is the most mature and probably the most refined way of ensuring that we're comparing apples with apples when we talk about the embodied carbon associated with buildings. So I wouldn't be surprised in the next year, 2 years, this will become an ISO standard that will become relevant within India as well. So if we think about, for example, a steel beam, you start off with your raw material supply. So that'll be your hematite within a quarry. The actions involved with quarrying out that hematite will involve, large scale plant, and all of those carbon emissions will be given the naming convention A1. So it will be called A1 under EN 15804. Maybe that hematite is then transported, and the transportation fuel and carbon emissions associated with taking it from quarry to a processing plant, those carbon emissions are given the naming convention A2. And then it's taken to be processed, and that specific processing carbon emissions will be given the naming convention A3. So this can happen several times over. I've only demonstrated sort of 2 moves here. But if, for example, something is transported from a quarry to a first stage of processing and then transported again to another stage of processing and then transported again to another stage of processing, it will be an A2 emissions, A3 emissions for the processing, A2 emissions for the transport, A3 emissions for the processing, until you get to the actual manufacturing of components, which is typically the end of that processing journey. So, for example, at the end of this A3 set of supply chain, you'll have a steel beam, a rolled steel universal beam, for example. When it leaves that particular manufacturing plant and is being transported to site, that transportation emissions, those transportation emissions are actually given another naming convention, A4. That's because it's outside of the control of the, in this example, steel manufacturer. The steel manufacturer can sell their steel beams to lots of different sites, but they won't necessarily have control over that A4 transportation emissions, and that's why it's given a slightly different designation. Now, when we've got our steel beam on site and we're putting it up into a building, we're using cranes, we've got certain wastage, there might be holes that need to be drilled on site, there might need to be paint applied on site, and those all have carbon emissions associated with them as well, and those are given the designation A5. So now we have our steel beam within our building. It's designed for 50-year design life, 60-year design life. Within that sort of operation phase, maybe the steel beam needs to be repaired. Maybe it was knocked by a maintenance vehicle, and there needs to be some processing to straighten out a flange or something. So the amount of carbon emissions associated with that repair would be given the designation B3, and all of the embodied carbon aspects of a building component in place are given B designations. Maybe it needs to be repainted, so that would also have carbon emissions associated with it. Maybe that's the maintenance one, so that's B2. Maybe there needs to be quite a major retrofit. So that particular steel beam is being replaced with two different ones. So there'll be a replacement and refurbishment sort of operations with that, and those will also be considered embodied carbon aspects for the life cycle there. This is also where we see operational energy use and operational water use, which are modules B6 and B7, and those are operational carbon emissions. Say, for example, the steel beam did get to stay in the building for the rest of its life, and now the building is being deconstructed. The act of deconstructing the building and the craneage and lifting that steel beam out of place will be given the designation C1, and then any transportation at end of life will be given the designation C2. Any waste processing, for example, the removal of the paint that it had on it, or maybe it needs to be chopped up a bit to be transported further, all of those kinds of things will be given the designation C3. And then if the steel beam is thrown away, there will be certain carbon emissions associated with landfill. Very little for steel. This is more applicable to timber, where if timber is disposed of incorrectly, it can rot and emit greenhouse gases as part of its rotting, and those will be given the designation C4. Or in the case of a steel beam, it's got a really high reuse and recovery potential, but also a high recycling potential because it can be smelted again and used to make a new component. And this kind of new life aspect is given the module D designation. Because module D kind of sits outside of its original life cycle, it's usually reported quite differently. And it should be reported differently because it can start to muddy the waters if you're really trying to compare apples with apples when you're looking at building components. So if we were to just look at modules A1 to A3, that's given the name cradle to gate, which might be familiar with a couple of you. This is because A1 to A3 is part of the supply chain for a manufacturer, and it's modules A1 to A3 that they'll have the most control over because they'll need to manage their supply chain. They will need to manage their energy and cost operations, etc. If they're selling a meter length of steel beam. So Tata Steel will have a really tight control over modules A1 to A3, and they'll be able to report these kinds of numbers with high levels of accuracy. And it's meant to be from the cradle of the earth to the factory gate. That's why it's called cradle to gate. If we look at all the A modules, A1 to A5, that's called cradle to practical completion. And that's also known as the upfront embodied carbon within a building. So everything up to handing your building over to the client, which we as structural engineers will have quite a large say in. Yes, we'll be working with suppliers who will know the A1 to A3 numbers, but we will then have a say in how locally sourced the material could be, but also how the material fits together within the building as well. If we were to look at the whole system, that would be cradle to cradle. So that's whole life carbon. That's the carbon emissions associated with the whole of the building throughout its design life. As structural engineers, we may be able to impact, how much maintenance the structure will need, how much repainting, those kinds of things, the likelihood of what needs to change if you were to adapt the building or have a flexible space, but also if the building was to be decommissioned, how easy it would be to reuse certain elements as well. However, we could plan for a building to be deconstructed or maintained or kept in a certain way, but ultimately it is up to chance as to whether or not a building will stay in its current state for 50 years, or potentially we'll put together a building and then after 10 years it's not fit for purpose and there'll be a major retrofit, which is always a risk as well. So measuring carbon and the data. The embodied carbon calculation itself is relatively straightforward. What makes it complicated is the fact that calculating specific material quantities, understanding exactly which carbon dioxide rate to use, and then summing up all of the different embodied carbon quantities at the end. There's lots of different elements that go into a building. There's lots of different people that are involved in putting together a building. And so the complexity comes in with the fact that we need to do this calculation many, 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 many times. When looking at material quantities, it could be hand sketch, it could be a Revit model, it could be a bill of quantities from a cost model as well, which is something that we're using a bit more for sort of more official auditing of embodied carbon in our buildings. We're going off the cost model so that it's easier to align what's been costed and what the embodied carbon is, so that there's no sort of, less uncertainty as to actually what's been modeled for that. For the CO2 rates, for generic materials, there are certain databases available. I know that in the UK there are a couple, and I know it's probably a bit more difficult to find in India, but I know that there are a couple of sort of more university-led databases available to you. But I think where you'll be able to find a bit more data is looking at specific product certificates for embodied carbon rates, and looking up environmental product declarations. So large manufacturers, for example, Tata Steel, actually do produce environmental product declarations, which give you the A1 to A3 carbon emissions for that particular product, or at least a range of products. And something that I would encourage you to do is even just ask suppliers, oh, do you have an EPD, environmental product declaration? Because I like to think that if enough people keep asking suppliers for this information, they'll step up to the challenge and put the time and effort into producing it, because they know that it's something that the industry is looking for. In terms of transportation emissions, again, apologies for the UK focus of this, but our government actually releases greenhouse gas emissions each year for fuel mixes and for different modes of transport as well. That's from our Office of National Statistics. What I have found in the past is, even if I can't find a country-specific database for things, I try to find a database that at least has some data in it, and then take that with a pinch of salt, add some sort of uncertainty factors to it or margins of error, because at least those kinds of figures will give you the right order of magnitude, typically for these kinds of calculations. Then with reporting CO2 quantities, typically we report kilograms of CO2e per meter squared of gross internal area. That's how a lot of our colleagues and also other sort of project team members can understand it. And that's also where we're seeing a lot of targets being set, is on the meter squared GIA. Within Bureau Happold, we have our own structural embodied carbon calculator. It made sense for us to develop our own because then it can be embedded within our own processes, our own QA procedures, but also within our own reporting templates as well. We can report sort of total kilograms of CO2e. So as you can see from this, I didn't want to pretend that Bureau Happold's projects are all sort of like A's and B's, because they're not. You can report the total kilograms of CO2e for a project, and we have a really large discrepancy between the kinds of projects that we calculate the embodied carbon on, and that's by virtue of the fact that we work on some really large scale projects, but also some really small scale projects as well. And I think it's important to share that we've still got a lot of learning and a lot of progress to make as well as structural engineers. There's also potentially a way of reporting embodied carbon that makes sense for that particular sector. So, for example, embodied carbon per student for a university, or per person term for a school or university as well. In terms of stadia, it might be that you want to report your embodied carbon per seat of that particular stadium as well. So there's lots of different ways that you could report it, and it's possible that per meter squared GIA isn't the most appropriate, or even the total is most appropriate. So yeah, bear that in mind. In terms of looking at the calculation in total, there is some really good and freely available guidance on the internet. I would say that the RICS, which is the Royal Institute of Chartered Surveyors, are leading the way, I would say, globally. I haven't seen such a comprehensive one-stop shop for calculating whole life carbon within buildings as this particular guide. It is 240 pages long, so pretty long, but it's really in depth. And if you are interested in this, I would really strongly encourage you to have a look at that, because I think that it will become more of a global document as the years go by. There are also ways of looking at the system and also getting data for modules from sort of online and also web-based tools. So there's things such as One-Click LCA, which is the one that we use within Bureau Happold. We predominantly use it in the UK, but our European offices also use it as well. And then there's also eTool LCD, which I don't have as much experience of, but I didn't want to essentially just talk about one tool for this particular topic. And then there are also system processes for different disciplines as well. So the Institution of Structural Engineers has the second edition of how to calculate embodied carbon. I would also really strongly encourage you to have a look at that. I believe that's free to download too. There are also system process guidance documents for MEP engineers, mechanical, electrical, and public health. That's what we call mechanical engineers in the UK. So that's TM65. And then there's also system processes for infrastructure as well. So PAS 2080. So that's carbon management. It says in buildings and infrastructure, but it's predominantly used for infrastructure. But yes, I would say that the RICS guidance gives a really good explanation. And then also, yes, of course, the for the structural engineers on the call, I would encourage the Institution of Structural Engineers guide as well. So that's a lot about the theory, a lot about what it is, what embodied carbon is, our responsibilities, but actually, how do you translate this into something that you can do on your current project? The key thing I want to get across is that the earlier you talk about embodied carbon, the more impact you can have. So this carbon reduction potential graph was actually produced by a couple of sources before being adopted by the World Green Building Council, which is, a global a global entity. And they used this particular way of talking about reducing embodied carbon in their report called Bringing Embodied Carbon Upfront. And they suggested 4 different ways of reducing the embodied carbon of your projects. The first one is to build nothing, and then to build less, build clever, and build efficiently. So I've actually grouped together the build nothing and build less for this particular presentation. And then I will talk about build less in terms of retrofitting existing buildings, because I'm sure that there are already circumstances where existing buildings are needing to be retrofitted within your portfolios. Then I'll talk about building clever, so things like challenging criteria and low carbon materials, and then finally building efficiently as well. So it depends, regardless of how far along your current project is, you can make a change tomorrow or today, depending on how late you work. So I also wanted to highlight, I had a look at the IA Structees Code of Ethics, and I was blown away by the fact that this is the first sentence. So yeah, that's really encouraging for me. Yeah, it's to ensure structural safety and to achieve a more sustainable built environment. So I take this sentence within your code of ethics to really encourage you to shift your mindset from we can solve a problem to how can we remove a problem altogether. And this is where I think, challenging, do we need to have all of this building? Do we need to have this building at all? Is actually taking ourselves to that mindset of designing something to actually leading sustainability of the structure. Clients hire structural engineers for their knowledge and understanding of buildings, and being a trusted advisor means steering the conversation and leading talks on sustainability, and really taking that opportunity to interrogate the brief and interrogate whether a problem is worth solving or if we can design out the problem in the first place. To kind of put it into more sort of pragmatic terms, it's really sort of looking at the brief, and the brief is typically an interpretation of what the client thinks can solve their problems, but it's up to us to suggest alternatives and prevent excess space being created in the first place. So, for example, can you revise the design for so it's better suited to reuse an existing building that exists elsewhere? Can the design or the brief that you've been given be changed so that some elements double up on functions? Like, do you need to have a separate lecture theatre to exhibition space? Like, could certain functions double up, and so actually you get to cut down the total GIA in the first place? And it's through our knowledge of how loading requirements and space requirements, etc., that we can make suggestions where, oh, this particular function is actually quite similar to this function, and you need to have both functions in your building, Ms. Client. Have you thought about potentially combining the two? I would say that those are the kinds of conversations that us as structural engineers, as leading sustainability, should be having with our architects that we work with. Another comment could be, can some elements be temporary throughout the year? Um, if there are spaces that are only used for example, for 2 months of a year, does it have to be a dedicated permanent structure for that quite low utilization? Or could temporary structures be built up and taken down for some functions within a building as well? When I first had to think in this way, I found it quite challenging. So it's not something that I think that people can change about themselves tomorrow, but it's worth having this in the back of your mind and um, taking the opportunity to challenge when you feel like you know the client enough to be able to do so. And that kind of takes us on to building nothing, building less, stretching client aspirations and really knowing your client. So to reiterate again, clients hire designers and consultants for their knowledge, insights, and creativity. And that's something that we as structural engineers have. And that's why clients hire us. I would say that, us as trusted advisors, it's worth us trying to find our client's limit for a departure from business as usual in relation to embodied carbon through frank discussion and also showcasing all options, not self-censoring. This is something that I've definitely seen in myself and I see in certain colleagues as well. And it's worth sort of highlighting and being aware of where you see it in yourself. Showcasing all the options, always showcasing the most efficient option for a project is worth doing. All projects are a balance though. But even though it's a balance, it's worth finding a strategy that's a stretch, but not a strain on the client. And these kinds of conversations, these frank conversations about finding where your client's limit is best achieved through knowing your client and nurturing that relationship as well. So the diagram that I've produced on the right-hand side there is your client will have somewhere along that sort of axis of, do they just want to do the minimum? Do they just want to achieve what's in the regulations? To be fair, that's fine. But it's definitely worth sort of discussing different ways of achieving best practice, ways of showcasing innovation potentially. And along that particular line, you'll find the client's stretch goals, which balances the client's constraints, balances the client's value, and is good practice for that particular client as well. There's also, it's not also a case of you have one conversation and then it's done. For particularly long span projects, maybe large master plans, definitely infrastructure projects, but also certain buildings might just have a slightly longer time frame. It's also worth being aware that you can allow room to improve as well. So at project kickoff, it might be that you're at regulatory sort of stage, but different externalities may come in. There might be a tightening of minimum standards for that particular sort of type of project. For example, offices might design to a certain office standard, and there might be a tightening there. There might be updates to other design guidance. That client might actually have hired a new sustainability team or a new ESG team. And it's worth being aware of these kinds of externalities and having a project touch point and discussing with all of these that have come into play. Is it worth maybe revising our sustainability targets or embodied carbon targets that we might have set for the project. Other externalities might be things such as award-winning case studies that capture the imagination of a client. I've definitely seen that come about. There's been, industry press about award-winning projects, and then clients ring up going, "Have we thought about potentially doing this?" So definitely take those opportunities. There might be updates to national targets, and there might be sort of new leadership as well. And it's worth revisiting these conversations, which is more possible if you have that good relationship with your client as well. Moving on now to sort of more building less, so reusing buildings, so retrofitting buildings. Again, this requires a bit of a mindset change. So typically when we build new, we would have unchallenged requirements. Maybe there'll be certain challenges, but essentially we produce a new building to suit those requirements. When we're retrofitting, we have our existing building anyway, and it does mean that we need to adjust our requirements for that building, which can be a bit of a sticking point. And it also just requires a bit more discussion up front. And again, this is where the structural engineer has a really key part to play as to whether something is viable or not within an existing building. One way I like to talk about reusing buildings is through Brand's model of building layers. So the shearing layers within Brand's model, because reuse isn't a case of you have to reuse everything or demolish everything and build new. There's lots of different levels of intervention that we can make when reusing buildings that vary in permanence. So the people inside, the stuff in the space plan, all quite fluid. Might be maybe the space plan has like a 2-year, 5-year kind of design life. Then you've got your services and your facade, which varies between 15 and 30-year kind of design lives. And then you've got things like your structure, your site and surroundings, which are much more permanent. So if we look at reuse in buildings, just looking at the people flow, the stuff, and the space plan, I want to share with you an example that our Bureau Happold analytics team, who do people flow modeling, shared with me for the UCL Institute of Neurology. So this is a neurology institute in London, in the UK. The feasibility layout was put through the people flow modeling software, and there was a uniform potential for interactions. So as you can see, kind of around that atrium area, it's a bit more orange. So that was where the most interactions would have potentially happened. And then there's some other quieter spaces towards the corners, etc. But through sort of iterative design, the proposed layout, sort of data led from analytics, came up with this particular layout that really gave a dynamic set of spaces within this floor plan to really sort of highlight hotspots for interactions and vibrancy. And then also increase the number of quiet spaces as well for deep work. And also, depending on what you're working on, you might need a quieter space, or you might want a slightly more vibrant space because you need some external inputs to figure out a problem. This also is a lot more appropriate for neurodiverse people, people who have auditory sensitivity. They might not do well with a low hum of noise around them. They can then find spaces which suit them better for work as well. So this, in my mind, the diversity of spaces has made it a much more inclusive design as well for people to work in. For reusing buildings, it might mean actually just kind of changing your building control systems. So we've got another service offer within Björhapel called Smart Buildings and Control, which diagnoses your building and adjusts your control systems. So actually, you might not need to upgrade your services and MEP systems. You might just be able to manage what you already have in a better way to reduce your energy consumption and actually make the space much more comfortable to be in. This is an example from our Edinburgh in Scotland's offices. Previously had a very uninspiring, I would say, office building, as you can see in the photo at the top there. They had out of date building services, a lot of rooftop plant as well, and a really poor performing facade. So the building services were old, the facade was poorly performing, so it was getting a bit too cold, and yeah, the amount of space dedicated to plant was not acceptable for the building owners at that time. So actually, with an upgrade to the facade and an upgrade to the building services, a roof extension could be added. All of the really heavy plant equipment at the roof could be removed, and a restaurant and viewing deck was added at the top. So increasing the GIA of the office, increasing occupant comfort, but also, yeah, just making the building work better for what they wanted it to do. And then another sort of example of reuse. This is a multidisciplinary Björhapel project again in London called Here East. So before it was the kind of main control centre for the London 2012 Olympics. And what happened was the facade was replaced to allow for a lot more daylight to come in. Mezzanines were added, and now it's a really vibrant sort of workshop and dance studio and startup space in London. And a lot of the structure stayed as a result of surveys, testing, assessment of the loading requirements, assessment of whether or not certain spaces would be appropriate for a change of use. So the structural engineer played a very big part to play, even if the amount of time and effort spent doing calculations and verifying things didn't necessarily translate to adding new material as much as it would do with a new build. But structural engineers who understand buildings, who understand how buildings fit together, we're using our brains to figure out this viability without necessarily designing new and adding new stuff. Moving on to building clever. I want to share with you the impact of a building grid. So regardless of if you are going to go down a new build route, regardless of what material you're going to use, really interrogating what your structural grid is a really key. It's a really key thing to kind of bottom out and to try and reduce your grid to what's appropriate for the use, but also what works efficiently. And this is material agnostic as well. So regardless of whether you're designing in concrete, steel, or timber, you can have quite significant embodied carbon reductions that you can demonstrate. So the numbers here are for a very standard UK design office. So we had a 9x9 grid in concrete, a 9x9 grid in steel, and a 9x9 grid in timber. And those were respectively 331 kilograms of CO2e per meter squared, 227 kilograms of CO2e per meter squared, and 142 kilograms of CO2e per meter squared. And in each of those instances, when we reduced the column grid to 6.5 by 6.5, we saw significant embodied carbon savings. Yes, there was an increase in the number of columns needed, and So if you were to look at the embodied carbon of just the columns, that did increase. However, the floor plates and the material required for the floor to span between columns was much less. And if you can reduce the thickness, or at least not reduce the thickness, apologies. If you can reduce the amount of material used within your flooring systems, that will have a significantly increased benefit to the embodied carbon of your project. And it vastly outweighs the additional material needed for the columns and subsequent foundations as well. Really targeting the material within your floor plates is key. The impact of building height. So there's around about sort of a sweet spot between 3 and 6 stories for the embodied carbon of buildings that increase in height. So the reason that this is so this study was done for a concrete frame building. The reason that this is because the taller the building gets, the more material you need for your foundations, your typically piled foundations in this case. And then also the more space within the building overall is dedicated to your lateral stability and your core systems. And so the less space is available for your GIA. So the less usable space is available, the taller you get. And so that has a significant impact on your embodied carbon per meter squared. So even if you can shave 1, 2 stories off a high-rise building that you have, you can make significant savings in the embodied carbon of that. In terms of questioning adaptability, typically when we sort of receive briefs, we see the word adaptability, and it's always worth questioning what the client means by that. A lot of the time we will potentially put in an initial redundancy. So the building might adapt for a change of use. So you add a bit more capacity for a change of loading, and you add redundancy to the columns and the slab. When actually the adaptability could be achieved through adding redundancy to the columns and foundations only, and having a mechanism by which the slab can be strengthened, either through carbon fiber reinforcement, or potentially, if you're looking at steel constructions, having enough space between primary beams that you can add additional beams as well, and additional columns where appropriate. And actually what we found is through, an additional redundancy of columns within your columns and your slab, this was approximately in our sort of very standard concrete frame building that we used to test all of these hypotheses. That was around about 349 kilograms of CO2e per meter squared. But then with a future strengthening approach, that was a total of sort of 302 kilograms of CO2e. And that's because we left the opportunity for the slab to be strengthened. So we're still achieving the possibility for adaptability, but we're not adding the carbon now. We're not adding the redundancy now to the slab. We are to the columns and the foundations, but not to the slab. And actually, not only does this have an embodied carbon saving, this also saves material in the first place, and it saves your client money as well, because you're not adding material to the building that may or may not needed to be there. Building clever as well, lean versus resilient design. Again, this is not necessarily about blanket over design. It's about actively considering what will be needed for so depending on if you're looking at Eurocodes, British Standard, etc., you might be designing to a 250-year design life. But you can achieve resilience with a lean design as well. And there's a really good paper available within the iStructE written by Caroline Field, which I also believe is free to access. Another way of building clever is to challenge criteria. So, as we mentioned before, challenging space requirements, challenging column-free spaces to really reduce that structural grid, challenging loading requirements as well. So, for example, air handling units within the UK typically fall within plant loading, which is typically taken as 7.5 kilonewtons per meter squared. But actually, the weight of air handling units is typically around about half of that. So, really clarifying and refining what is going into your plant rooms can yield quite high savings in loading, and which can yield savings in material, etc. Also challenging serviceability requirements as well. Could you add a pre-camber to any steel work so that you can reduce your deflections? You know, in terms of additional heating requirements for stadia. So this image at the bottom, which 12 degrees C. On the right hand side is I think it's a stadium in Spain where at 12 degrees they turn on space heaters, which has increased weight. It will add more weight to the roof, etc. Whereas 12 degrees definitely within the UK is not considered that cold. So you'll have people in shirt sleeves at football matches. Another sort of way of challenging criteria is more people do work from home. If you're going to be producing an office for 100 people, do you need 100 desks, or could you get away with 50? That kind of challenge as well. More about sort of interrogating loads. Within the UK, we have some of the highest office loading within Europe at 3 kilonewtons per meter squared. Whereas in different areas of Europe, they reduce to sort of 2.5 kilonewtons per meter squared, or even 2. And actually, when you have a look, like with the image on the right-hand side here, actually what 3 kilonewtons per meter squared is, it's quite amazing when you see it in real terms, what those kinds of loads actually look like. So it's worth bearing that in mind as well when you're doing your designs. Also having a look at whether or not something is SLS governing or dynamics governing, and really trying to interrogate whether you have to add mass for that, or whether there can be different ways of relaxing the criteria, or other ways of achieving the criteria set out as well. A different way of also looking at loading is to actually match the loading to your building as well. Seems pretty self-explanatory, but I don't think that we challenge this kind of thing enough. Really trying to keep your heavy loaded things at lower levels, things such as storage, server rooms, etc. And then keeping your lighter loaded things at the top as well. Obviously, roofs would be at the top of your building, but also things such as, classrooms, restaurants, etc. Yes, there's quite a lot of variety within those kind of green classification of loads there, but there's still a lot less than the kind of the orange sort of mid loading categorization that I have here. Things like dance studios, gyms, exhibition spaces, etc. Next is to sort of specify the right material for the job. Sometimes when people are starting out talking about embodied carbon, they look at kilograms of embodied carbon per kilogram. of building material, which is actually a bit of a red herring. As you can see on the diagram on the left-hand side, concrete is actually a really low embodied carbon material if you look at it on a per kilogram basis. But on the right-hand side, you can see that actually a concrete beam is 10 times as heavy as a timber beam for when it's performing the same function. So a weight of beam to span 7.5 meters, for example. And so you need to really look at how much material is needed to do that job when you're comparing the embodied carbon of different elements, whether it's a beam compared to a beam compared to a beam, or a slab or a column, etc. It's not enough to just look at the embodied carbon per kilogram of that material and compare on that basis. Moving on into sort of building efficiently, one way is to really refine your utilization. This isn't a case about under designing. This isn't a way of justifying unsafe practice. This is a way of refining your utilization appropriately at the appropriate design stages. On the left-hand side, we've got imposed load reduction. This is something that we can do within our codes. Apologies, I'm not as aware of a possibility within your codes. But when you've got loaded areas of over 10 meters squared per grid and also over 3 stories, you can reduce your the imposed load on your or live load on your floor plates. This is born from this kind of probability that the probability of all those different maximum live loads being applied to your floor plates all at the same time. And so you can take advantage of the extreme unlikeliness of that by using these reduction factors. And then on our right-hand side here, these are our target utilizations and utilizations not advised within our designs. And it's not necessarily about the most utilized elements here. It's about looking at your least utilized element and really trying to increase its utilization so it achieves that minimum. So for example, if you're at design stage, or sorry, if you're at detailed design stage or your technical design stage, look at the beam that's performing the least or carrying the least loaded area. Is it working at 50% utilization? If so, is it possible to then reduce its size so that it works at least 75% utilized? It's about looking at the lower end rather than asking people to design unsafely at the upper end. I really wanted to stress that there. Another way of building efficiently is to use geometry. Again, regardless of which material you're building with, you can find ways of using that material that make use of structural depth where appropriate, so that you use the material wisely. Pushing for trusses rather than deep fabricated box beams. And typically, if you do use less material, it is a low carbon solution. And then also optimization as well. So design freezes and design optimization stages and programs. I know that this is very rare. I do work on projects as well. But it's worth pushing for design freezes. It's worth pushing for design optimization stages within your design program. And this is because it is at that stage that we can really look at our underutilized elements and ensure that they come up to at least a basic 75%, depending on your particular project utilization, so that you can make efficient use of material. And then the arguably slightly more exciting area of optimization, really trying to use advances in 3D printing to only put material where needed, and also advances in computational design as well for optimization, and sort of parametric modeling there as well. So, moving on to beyond embodied carbon, there's this really good diagram that was shared to me by a colleague called carbon tunnel vision. And carbon emissions are relatively easy to measure, and so people can get carbon tunnel vision because they think that if they keep the carbon low, um, their project will be sustainable. When actually, even though it is one of the most important things to reduce within your project, um, it's very mindful to be aware of sort of general overconsumption, biodiversity loss, water use, inequality, and all these other areas of sustainability that we need to keep in mind as well when we're pulling together our buildings and, really challenging the brief at the first place. What I like to talk about is the carbon worth the spend? So, what value are you adding with that embodied carbon spend? For an inclusive, sustainable, and appropriate design, reducing the embodied carbon of that project must be balanced with the value that design decision can provide. So, for example, within the UK, if you're building social housing, it might make sense to add triple glazing rather than double glazing so that you keep the energy bills low, and it works well in terms of energy efficiency. But if you look at triple glazing versus double glazing on purely a carbon basis, there's more material in the triple glazing. So the triple glazing would be more embodied carbon. But when you look at it in context, you can make the decision, or you can at least bring up the fact that yes, triple glazing may be more embodied carbon, but look at the benefit, look at the value that it's adding to this particular building. Other ways of discussing value could be inclusive design. What interventions are needed for an inclusive building? What interventions are needed for a high quality indoor and outdoor space? If we look at sort of regenerative design principles as well, are you positively impacting your users outside of the site itself? Are you positively impacting supply chains? And is your project having a wider impact than beyond your site for the better? And I think that a really good sustainability assessment method, if you're not already aware of it, that covers these kinds of things, looking at embodied carbon, but also looking at wider aspects, is the Living Building Challenge. And they ask, what if every single act of design and construction made the world a better place? What they look at within this particular sustainability assessment method are things such as place, which really, I think, characterizes the fact that our designs and our architecture need to be born from where they're sat, rather than identikit sort of office buildings, across the globe. Really looks into water usage, looks into energy. Buildings should generate 105% of their own energy. It looks at health and happiness as well. It looks at materials in terms of embodied carbon, but also looks at embodied toxicity of the materials as well. It looks into equity, and then also looks into beauty, which I really like. If a building is beautiful, you're more likely to look after it, you're more likely to retrofit it in the future, and more likely to care for it. And I think there's a lot to be said for really sort of treating our buildings with care, repairing them, looking after them as a low carbon act as well. So, in summary, um, all of the different sort of pragmatic approaches I've given you sort of look at reduction due to interrogation and brief, optimizing design loadings, etc. Don't do them in isolation. It's through the cumulative impacts of this that we can actually make significant savings on our buildings. And then key things to ask yourself, am I discussing sustainability early enough? Am I interrogating all assumptions? Can I just use less stuff within the structure of my building? Tackle material savings on floors. That's really key. Looking at upfront carbon emissions, so A1 to A5, and then also thinking about the value that that carbon is adding to. So thank you very much for listening.
Thank you very much, Dr. Watson. Such a fascinating presentation,
Thank you.
really appreciate. I think you have covered this subject in entirety,
Yeah,
and also
talked a lot.
made it so comprehensive. You started from the very basic and went on and practically touched almost all aspects that a structural engineer needs to look at from the consideration of sustainability. I think one of the very few excellent presentations I have seen in
Oh,
you
thank you.
know uh, recent times. Now, I would like to take few questions. You have already got a lot of bouquets from participants, uh, sort of expressing their, um, you know, your presentation has been very well appreciated. So let me take up questions. First, let me just read from Q&A. The
Hmm.
first question is from one of our climate warrior in India, Vijay Kulkarni.
Hmm.
How to convince producers of building materials in India to provide their EPD?
Yeah, it's a very good question. Um, so an approach that we've been doing is even though it might not have as much of an impact on the final decision as maybe we'd like, what we've been doing in our specifications has been saying supplier to provide an EPD as part of the specification. Um, and through the ask of wanting that information, um, our main contractors, when going for tender, will ask the questions of suppliers. And sometimes it works, sometimes it doesn't. But if the suppliers feel as if they're falling behind because other people have done it, um, it's in their business interest to at least provide some numbers for their materials. It's a it's a slow process, and you need that groundswell. I think it so EPDs came into um, force, not force. They came into the UK around about 2016, and it was only around about 2020, 2021 that you started to see a lot more. So that's 4 or 5 years essentially. Um, I think it should be quicker. In India, you could always threaten that you'll use a another supplier from another country, but again, it might not work well that way. Um, it could be that if you have high sustainability aspirations on a particular project, you mention as part of that, well, we need to be certain of the numbers that of we need to be certain of the embodied carbon we're going to put in our building. And to do that, it would be great if we had EPDs from any supplier that's going to be working on this. And then it sort of takes that sustainability golden thread all the way through to what's going to be actually built on the site.
Okay. I think, Natasha, you also mentioned in your presentation somewhere that, even if you don't have the precise numbers, but if you want to really compare between three or four alternatives, you can work with any number as long as relatively, the uncertainty factor you can put in available numbers and work with it.
Yes, exactly. So, I mean, we've done a couple of projects in the Middle East, and the amount of information available in countries like Qatar, etc., for for the embodied carbon of concrete or the embodied carbon of steel, it's been difficult to find. And so what we've done is uh, used numbers from an area close by and used those as a standard number, and then compared different options using those numbers. Um, Also, if you don't, and that has helped us inform our decisions. And as long as you're very clear and transparent when you're using those numbers, that will be fine. I think transparency and working within the limitations that we have is key. Um, if that doesn't sit right with you, typically material weight and mass per meter squared of a particular structural option is usually a good proxy for embodied carbon. Um, so using material weight uh, is a viable alternative as well. Like 90% of the time, the lowest weight option will be your lowest carbon option as well.
Okay, thank you. Thank you. Next question is from Mr. Deepak Bansal. Can you please elaborate more on the recurring embodied energy, as this is found to be more than initial embodied energy in life cycle assessment?
Yes. So if you're so depending on the efficiency of your building in terms of heating, cooling, electricity, etc., and also depending on your energy mix, um, there'll be different carbon factors associated per kilojoule, kilowatt hour within the operation of your building. I had a quick look at India's energy mix, and I think you're at 80% fossil fuels. So if you were to do a life cycle assessment within India using a typical Indian fuel mix, you're more likely to have higher operational carbon over the life cycle of your building than embodied. Um, However, with increasingly efficient building systems, such as LED lighting rather than alternatives, if you've got high performing facades, so you reduce your heat loss and heat gain, the amount of energy that you'll need to heat and cool your building, which is typically the largest percentage of operational, will reduce. And also, there'll be more and more renewable energy made available in India. So that will also reduce your operational carbon in the coming years. And so it means that embodied carbon will have more and more of um, a, a larger percentage within your buildings, within your new build buildings anyway, as time goes on. But that's the reason why operational carbon is so much greater at the moment within LCAs.
Yeah, thank you. We have a question from Dr. S.P. Anchuri, who is both architect as well as a structural
Ah,
engineer.
cool.
Very rare combination. And he is asking in general why architects are comfortable in making built environment sustainable, but structural engineers not. Are design codes supporting which play a significant role in guiding towards reducing carbon footprint? They have limitations because of their prescriptive nature, lack of flexibility, focus on safety and performance, and limited coverage. So I think he's talking about the architects perspective and the engineer's perspective?
I think that definitely from I can only speak from my experience with this, but the most efficient structural system is likely to be the lowest carbon system. And historically, it's been an eternal struggle between I'd like a 6 by 6 grid or I'd like an 18 by 18 grid. And having increased structural depth within your floor plates so that you could have material where it's needed. Our floor plates, our structural zone within our floor plates often gets shrunk, which adds more material. I think structural engineers know more about how to reduce the embodied carbon of the structural frame than they think they do, because it's not been framed as a way of reducing embodied carbon. There's still I would say, a misconception that the only sustainable building is one built out of rammed earth or timber. And actually you can make massive savings in embodied carbon if your concrete frame is able to have an efficient system, minimizing transfers, minimizing cantilevers. And those are things that I would like to argue structural engineers want to do anyway as well. We want to have clear load paths down to ground. We don't like inefficient structures. And it might be that the discussions with where the structural engineers remit for reducing embodied carbon have been had, it's been dismissed as going against the architectural vision, when actually it's the twin skills and capabilities of architects having a vision and producing space that can be loved and is usable and is appropriate. And then the structural engineers' in-depth understanding of efficient systems, having those full and frank conversations where you can work together is where we can see this kind of dynamic being used appropriately and for the best thing for the project and for the world as well.
I think you have put it very, very nicely. Very nicely. And I just want to add that, structural engineers have much more potential to reduce the carbon footprint in a building.
Mm.
And it's just that, we do not have the framework in place to do that. And I think, but once structural engineers become active and we have the necessary codes and standards and guidelines, I think we have much greater potential to reduce carbon footprint in any structure, be it bridge or building or anything.
Of course.
But that question was very, very nicely answered by you. Thank you very much.
Thanks.
Next is a question from Mr. Mohammed Sinokrut. How can we get the slides, please? I think she has already answered that. You will get a handout of this presentation. Another question from Dr. Anchuri. What are your views on good structural design reduce carbon footprint? Is builders and contractors demand always to reduce the iron or reinforcement quantity, which also contain carbon. Their interest is not to reduce CO2, but the cost. What are your views on good structural design, reduce carbon footprint? Yeah. So what he's asking is that while the builders, you want to reduce cost, and in a way it may be reducing the carbon footprint, but what is your view, whether that is the right way or?
I think that, again, from my perspective working on projects, contractors or builders will be aware of updates to different materials or different construction techniques that maybe we're less aware of. And it's worth having the conversation. But and if there are certain builders that want to shave a bit off here or remove a bit there, etc., I think it's up to us to look at that solution and go, actually, because of our analysis of models, our calculations, that particular solution is inappropriate because of these reasons. Or if they have proposed minimizing a bit here or that kind of thing and have justified a slight reduction. And actually, it means that that particular element goes from 75% utilization to 80. I think it's in our interest to potentially accept it. It's very difficult because it has to be on a decision by decision basis. Obviously, you will get some builders who will say that, say something wild, like, oh, you don't need foundations in that bit because my previous building is still standing up. And it's when you sort of see that kind of thing that you really have to obviously put safety first and go no. But I think that there are some builders who have some very good experience in making savings in material in certain ways as well. And it's worth listening and having that technical discussion about it, I would say.
Yeah. So I think you have answered his question, Emily. It is not just the reduction in material that is important. It is also important that you come out with an alternative which reduces the overall carbon footprint. So when it is a question of reduction of carbon footprint and embodied energy, it is not just the material reduction alone. It is also a material selection and the concept. But everything has to be done with safety in mind. You can't compromise on safety in any case. Next question is from Mr. Vijay Kulkarni. How to create the national benchmark levels of embodied carbon?
That's a tough one. Yes. So I would say that it's worth getting some of the bigger structural engineering firms in India that work a lot in India to calculate the embodied carbon or ballpark figures of embodied carbon of your projects in the past 2-3 years and see where business as usual is. And then from that, make a judgment on whether you could target 10% reduction, 20% reduction on that number. That's how we would approach it if we were to have a client that's got a portfolio of buildings. So we would have a look at their last 5 buildings and do a calculation. Have a look at where that would sit within benchmarks within the UK at the moment. But if they are producing bespoke buildings, it's possible that, an office benchmark won't be appropriate. So we would have a look at what their business as usual is, and then try and target a 10 to 20% reduction. So that, again, it's a stretch, but not a strain. You want it to be achievable, but you want people to have had to work to achieve it. If it's too easy, it's not making any change. But if it's too difficult, people become disheartened and don't want to try at all, because psychologically, sometimes that does happen. And so you want it to be the sweet spot. And I would say 10 to 20% reduction is a good sweet spot.
Thank you.
Cool.
Next question is from Mr. Naresh Sinha. Balancing of objectives. Do nothing, do less, or 50% or 100% reduction. have to be done at planning stage. Change of scope after inclusion in planning is very difficult. Therefore, we should insist on having carbon zero experts in each office and planning body, a thought for consideration.
So we're seeing more embodied carbon and net zero carbon experts in our local authorities in planning in the UK. That's only in the last year and a half. So I agree. Um, and what we're finding as well as structural engineers in the UK is we're getting involved at planning stage. We're getting involved at so we go by the REBA stages, but we're getting involved in that brief setting stage, which is the first time in, you know, I would say our careers that we've been involved that early on. And it's a novel space for us. Um, and I think there's a lot to still learn about where the uncertainty lies, but it's really encouraging the fact that structural engineers are getting involved that early. But again, trying to balance the uncertainty, because we're used to having a building and solving problems. So uh, it's exciting and novel, and is definitely a stretch rather than a strain for me as well. So yeah, I would say I agree. You need to have carbon experts and potentially structural engineers involved early at that brief setting stage to be able to show what is possible as well.
Okay, I mean, I want to ask a question now.
Okay.
What is driving this change, in UK? I just want to know, is
Mm.
it the client who is driving this change so that all the, as I can see, the environment, the ecosystem in UK, where I think the consultants are also getting geared to do this kind of calculations, they will feel out of place if they are not into the sustainability business. Now, who is driving this change? Is it the government who is driving this change? Is it the client? I mean, the contractor, institutions?
So I would say that initially it was driven by designers and architects.
Okay.
Our Architects Declare network within the UK is very strong, and it's gotten to wanting to change policy. And architecture and buildings, uh, from an architect's perspective, um, they're very good at writing sort of public consumption news articles, thought pieces about our built environment. So they capture the public's imagination in a way that I wish us as engineers could do a bit more. Um, and as a result of that, um, you are seeing a lot more of the general public being aware of embodied carbon and campaigning for buildings that might be demolished to be kept from an embodied carbon perspective. Um, because of that, politicians are a bit more aware, but also clients are very scared about the public image of not being sustainable in certain ways. What we have found, though, I think in last year is you'll get um, clients as well as practitioners, as well as the general public, talking about sustainability and embodied carbon in ways that could be considered greenwashing. And we've now had um, legislation come through to combat greenwashing specifically. So it's been used as a being sustainable is shown as you're innovative, forward thinking. It's a really good marketing tool. And now the legislation has caught up so that you can do the marketing, but you have to have the truth and the weight behind it. In more of a sort of my specific buildings context, it's coming through from the client because they won't get funding for their building unless they can achieve certain carbon targets. And they won't get planning for their building unless they achieve certain carbon targets as well. So the planners have used their power as being able to grant planning permission on a local authority level to go, no, you need to prove to us it's sustainable because our constituents believe this is important. And it's been really encouraging to see. So that's where it's been a bit bottom up and top down from local authorities. So it's been a mix of both.
Thank you. Thank you. I like this term greenwashing very much.
Yes, yeah.
Thank you. Okay, the next question is from Diptimai Bhavantare. Is it possible to achieve net zero as all the carbon factors in module A1 to C4 are positive values?
So yes, it is possible to achieve net zero, but and as you say, all of them are positive values. As long as the sum of those positive values are below that 1.5 degree C kind of like limit ceiling, and then you offset that sum by planting trees or investing in renewable energy or buying carbon credits as well, then you can say that you're net zero. You can't say that you're absolute zero because, as you rightly put, it's all positive numbers. There are very, very few materials you can build with that have negative numbers. Those materials are typically crop-based building materials. So you plant them specifically to use them in your building. So things like straw or hemp can potentially be negative as long as all of the processing, harvesting, transportation to your site, etc., doesn't exceed the negative number because they've grown and absorbed carbon dioxide. So we're still not there yet, but there are a few materials that I would say are very slightly negative. But then as soon as you put them into a building, you're going to be adding plastering or roof materials, etc. So your overall building will still very likely be positive and would need to be offset if you're going to say it's net zero.
Thank you. Thank you. So there's a question from Mr. Kantanaga Rajesh. Building orientation analysis also helps in reducing CO2 emission. But coming to embodied carbon, as it is inbuilt with materials going with alternatives or sustainable materials may be costlier or may increases the project cost. Requesting your comment on the same. So what he's saying is alternative material may be costly, initial cost may be high. So what's your
yeah.
view?
So I deliberately didn't want to focus on specifically green materials because I think that there are so many savings and so many quick wins that we can make with our existing materials that we use. So many wins you can make with concrete, steel, timber, so many material agnostic wins that we can make. Low impact building materials do have a premium because they're typically produced in smaller quantities. They and so they don't have the economies of scale that large producers of steel and concrete benefit from. And I would also say that if there's also the green uplift, the green premium, because they know they can sell it for more money because it's green. So sometimes that can also be what makes the material cost higher. However, if materials such as hemp lime, straw bale, rammed earth are used appropriately, they can mitigate the need for mechanical systems because of their hygrothermal behavior. So they can absorb and release moisture and they can absorb and release heat in a passive way. But you have to work with that material and work with the geometries that that material allows you. Um, Rammed earth can be treated like a very low strength masonry. So, what kinds of buildings would you produce with that? Straw bales, again, would be that kind of really low strength masonry. Round pole timber, you have to have your double curvature, otherwise you're not really making full use of the actual strength that those kinds of elements have. Bamboo as well, very good axially, but as soon as you try and put it into bending or you know, shear it in the wrong way, it's not going to work. So they call for a much larger departure from how we typically build buildings, but that's not to say that we can't use them in the right way. If you do have a couple of single story elements within a larger development, really consider mud bricks and rammed earth. If you have pavilions or sort of outdoor sort of courtyard spaces that need a bit of shading or a bit of cover, then making use of the double curvature and using things like bamboo or round pole is worth having a look at as well. But I would say focus on the savings with your typical materials and use the green materials only when it makes sense to. Don't try and force fit the wrong material for the wrong purpose.
Yeah, agreed. Great. Thanks. I see there are many questions, but I think looking at the
Yeah.
time, I will just take two more questions.
Okay.
Other questions, maybe I will pass it on to you for
Yeah.
by email. You can reply later.
Yeah.
So, just two more questions I will take. One is from Mr. Rajiv Iyer, who is asking, while I am myself a proponent of climate change initiatives, I sometimes think that the concept of climate change creates a loop where increased loads from climate uncertainty is considered, uh, uh, while simultaneously encouraging the use of sustainable materials to withstand these loads, thus perpetuating a vicious cycle. Your views?
Yeah. So there are increased wind speeds needing to design for higher flooding levels. Yeah, climate change has increased our external loading factors that we need to take into account. But I would argue that it's rare that, um, depending on the kind of building, but it's quite rare that wind loading will be limiting in your design. It's quite rare that the flood levels would be limiting on your design. So I would say that tackling over design for things such as not refining your imposed loading appropriately or designing with too much space, the really sort of early stage build nothing, build less slides that I had, um, uh, will will still be available and possible to you and not impact the fact that yes, we do need to design um, for much more regular flooding events, much higher wind speeds, much larger temperatures as well. So, but I share I I understand the frustration. It can feel like you're in a bind. Um, and if you are designing buildings that, the wind loading is limiting, yeah, it's uh it's difficult. But typically those kinds of climactic loading conditions won't be limiting on the design.
So I'll take the last question today from Mr. Sunil Gorle. How much is the cost impact in terms of percentage from the standard previous building to achieve the sustainability goal? Are the private developers and end users ready to pay this additional price in UK?
So if it's a case of saving material, the price is, I would say, balanced. It does mean that You might need to spend a bit more on your consultants, which means that the structural engineers get a bit more fee. But if we can save money for the overall project by saving material, then it should be typically cheaper. If you're talking about the cost uplift for using sustainable building materials or those kinds of things, I think that those are the frank conversations that we have on a client by client basis and on a decision by decision basis as well. So recently, one of our clients did really want to use timber and a steel frame. And we produced those options, and it was a bit more expensive. And they took it away and decided against it. But we know that there is another office that they're going to be building next to this existing one, to this one that we're currently building. And we're doing everything in our power so that when we talk about it again, we're not going to say, oh, it was too expensive last time, let's not talk about it. We're going to say, is now the right time? And put it forward. And they have their own, they have different pots of money depending on where these are kind of like portfolio clients. If a project is going to really strive to be an exemplary project that they can use in their marketing, etc., they can tap into different pots of money for that project, not just their project budget. So it's a complex world, but there are some clients who think that the value that the increased cost will give them is worth the expenditure. And then there are some clients who will have a number in mind not to go over. And it's finding that number. If it's an extra 2% on the baseline, but it gives you all of this extra value, it will be, I would say, very unusual that you would find a client that would say no to that. But it might be 2% for one client, it might be 10% for another. And that's where you need to find that level. And it's so variable that it can only really be found out through conversations and early conversations and frank conversations where, we're all learning together. This is very novel. And I think it's important to share that it's an opportunity for everyone in the project team to learn as well.
Well, very well answered, and thank you very much.
you.
I think from this conversation and from your presentations, I think our participants and the structural engineers have realized one thing, that the role of structural engineer now has, after this climate crisis, we have to basically gear up and take a leadership role. As you can see from the conversation and from the answers that Dr. Natasha Watson has given, that it is not just the role of playing a subservient role to the architect for doing a calculation and giving the design, structural design. You have to influence your client, you have to influence your architect client or the owner client, and make sure that the building or the structure that you design, they are sustainable, there is reduced embodied carbon footprint, and that is a part of our role. So we have to take a more leadership role in the new environment where we are into climate crisis. With that, I would like to conclude today's session. A lot of thanks to Dr. Natasha Watson for such an excellent presentation and also responses to the various questions. A lot of bouquets you have received in the chat box I saw. And we have now a contact, and we would also like to bother you in future whenever we have this kind of conversation.
Definitely.
Thank you very much. And I would like to also thank all the participants for staying on with us, though it was supposed to be finished in up to 5 p.m., but we have exceeded by about 16 minutes. Thank you very much. And with this, I close this
Thank
session.